Okay, in this example, we'll deal with a related rate problem that involves an angle. All right, and here's the situation. An aircraft is flying. An aircraft is flying horizontally at a constant height of 4,000 feet above a fixed observation point. And we'll see the figure in just a second. At a certain instant, the angle of elevation is 30 degrees and decreasing, and the speed of the aircraft is 300 miles per hour. How fast is theta decreasing at this instant? And we'd like to express the results in degrees per second. This will illustrate a couple of things. So here's the situation. Okay, here's the observation point. The airplane is flying along at 300 miles per hour in this direction. It's at a constant altitude of 400 feet, and of course, as the airplane goes farther and farther across, this angle theta is going to get smaller and smaller. And so what we'd like to do is we'd like to find the rate at which theta is decreasing. So let's consider this right triangle, okay? And let's let this horizontal leg of this triangle, let's call it H for horizontal leg. And let's notice a relationship that we have that will involve theta, which is changing. The 4,000 is not changing, and H. All right? And of course, the relationship is tangent of theta. Tangent of theta is opposite over adjacent. So that's 4,000 feet divided by h. Okay, and so we have these two variables. We have h and we have theta. And we have h is, well, we could tell that h, I think if you look at this for a second, this is a third, well, we don't know I guess I should say we don't know the value of h, and I don't think we'll need to, but we know that as this plane flies this way, h is getting bigger, and the rate of change in h, dh dt, is 300 miles per hour. Now, the units are very, very important here, all right, and so we want to keep careful track of those. And finally, then, we'd have, excuse me, that d theta dt is a rate of change in the angle, and this is what we're trying to figure out. This is what we're trying to figure out. Okay, all right, so let's see. I think that what I'd like to do is I'd like to rewrite this to get everything out of the denominator so we don't get bigger powers of h here and stuff like that. That way I don't have to worry about the values of these things. But so let's take a look. Let's rewrite it this way. Let's multiply both sides of this equation by cotangent of theta times h, and that will cotangent, since cotangent is a reciprocal of tangent, they'll cancel one another out, and we'll have h is equal to 4,000 feet times cotangent, the h's cancel, of theta. Now let's take the derivative of each side. We want to find out what d theta dt is. We take the derivative of each side with respect to t, so we'd have the derivative of h with respect to t on the left is equal to, I'll take out the 4,000 as constant, so we can take that out of the derivative with respect to t of the cotangent of theta. And so dh dt is equal to 4,000, I've left out a 0 here, 4,000 feet. The derivative of cotangent is negative cosecant squared of theta. Remember, cosecant is the reciprocal of sine. times, remember this is a composite function. We have the cotangent of the function theta, and so we have to use the chain rule. So theta is the inside function, so multiply by the derivative of theta with respect to t. Since we're looking for d theta dt, let's solve this for d theta dt. I can divide by 4,000 feet. All right, and I can multiply both sides by a negative sine squared, because remember sine is a reciprocal of cosecant, and we'll have then that d theta dt, dt is equal to, all right, 1 over 4,000 feet, all right, times a negative sine squared of theta, all right, and then times dh dt. Okay, and then now we can just insert the things that we know about here. So d theta dt is going to be 1 over 4,000 feet. All right, and a sine, if I think about this right triangle, if this is 30 degrees, all right, the sides of the triangle are in the ratio. It's a 30, 60, 90 triangle. 1, 2 for the hypotenuse, square root of 3 for the other leg. So remember, sine is opposite over hypotenuse, opposite over hypotenuse. So this is going to become a negative 1/2 opposite over hypotenuse squared, because it's sine squared. All right, and d theta dt, or dh dt, is 300 miles per hour. All right, now we have sort of a mixed bag of tricks, a bunch of units here. I'm just going to clean this up just a little bit here. Well, I won't clean it up too much. We'll do that just on the next page. We have some problems. We have inconsistent units. We have feet and miles. We can take care of that. And remember, we want d theta dt in terms of degrees per second. So let's get consistent units here. So let me make a copy of this result here. All right, and let's paste it down here. All right, and so the first thing, let's get consistent units on this. All right, and so what I would do to get consistent units, I'm multiplying all of these together, is notice the relationship between miles and feet. We know that 5,280 feet is equal to 1 mile. So we could multiply this by 1 mile over 5,280 feet, or 5,280 feet over 1 mile. Each of those have the same numerator and denominator, so they'll be like multiplying by 1. But let's multiply here. If I multiply it by 5,280 feet divided by 1 mile, notice that I have feet in the denominator, feet in the numerator, miles in the numerator, miles in the denominator. So I'm done with that. All right. All right. The next thing. All right. And so I have. Let's simplify it. Well, I won't simplify it, but let me look at what we have here. We have then in the numerator, I'll have. Let's see. Well, I'll have a negative 1. Okay, negative 1 from here. I'll have a 300, and I'll have a 5,280. We'll multiply these out later. Negative, all right, everybody else is 1, so multiplying by those is not going to change anything. And then in the denominator, I'll have a 4,000 times, well, I have a 2 squared, is 4, times 1. That's it. Okay, and the units that we have left here are just 1 over hours. Okay, all right. So let's make a copy of this. And now remember, we wanted to get this in degrees per second. So let's do that now. Let's do that now. All right. If I do this, all right, now here's the thing that we have to think about. We first of all have to convert the hours to degrees. Remember, or to seconds, I should say. Remember that we have we have 3,600 seconds is equal to 1 hour. So I could multiply by 1 hour over 3,600 seconds, which would be 1 because both the numerator and denominator are equal, or 3,600 seconds over 1 hour. I'd like the hours to cancel, so I'm going to multiply this by 1 hour in the numerator, so that way the hours cancel, divided by 3,600 seconds. Sorry about the dog. All right, and that way this expression is worth 1, but the hours are gone, and I have it in terms of seconds at the end. All right. Okay, now there's one other thing we have to keep in mind here. One other is that remember that the derivatives of the trig functions, and we took the derivative of cotangent here, the derivatives of the trig functions work in radians and not degrees. So the angular measurement in this expression now is going to be in radians. We'd have to convert from radians to degrees. And so we'd have the relationship halfway around the circle is 180 degrees. I'm going to write it like this instead of the little degree symbol. And 180 degrees is pi radians. Notice I don't put anything next to the pi. Radians are considered to be a dimensionless quantity. That is, we don't write the unit radians down here. And so what I want is I'd like degrees per second, degrees in the numerator, so I'm going to multiply this by 180 degrees per pi radians. Okay, that's 1 because it's equal numerator and denominator. And so what I'll have here then is d theta dt. Notice the units that I'll have left are degrees per second. And let's see, what will I have in the numerator? I'll have -1 times 300 times 5,280 times 180. From way back here, the 1, of course, won't matter. When we multiply by 1, 1's a multiplicative identity, so it doesn't change anything. And then in the denominator, I'll have 4,000 times 4 times 3,600 times pi. And this will be in degrees. Degrees are the only units left in the numerator per second. Seconds are the only unit left in the denominator. And if you multiply this out, this turns out to be about a negative 1.576 degrees per second. So at that point in time, that angle of inclination of the sight line there is decreasing by about 1.5 degrees per second. Okay, the important thing to keep in mind is that when you deal with angular measurements and you're using calculus on them, you're taking derivatives of them, then you have to remember that it deals with angles as though they're in radian measure. All the formulas we developed were assuming that we measured angles in radians. Okay? All right, I hope this video helps.